Understanding basic wireless theory. To send data across a wired link, an electrical signal is applied at one end and is carried to the other end. The wire itself is continuous and conductive, so the signal can propagate rather easily. A wireless link has no physical strands of anything to carry the signal along, and how then can an electrical signal be sent across the air or free space? Consider a simple analogy of two people standing far apart and one person wants to signal something to the other. Okay, they are connected by a long and somewhat loose rope. The rope represents free space. The sender at one end decides to lift his end of the rope high and hold it there so that the other end of the rope will also raise and notify the partner. After all, if the rope were a wire, he knows that he could apply a steady voltage at one end of the wire and it would appear at the other end. The left figure, as you can see here, shows the end result. The rope falls back down after a tiny distance and the receiver never notices a change. Okay, this is the failed attempt to pass a message down a rope. And about the right figure, the sender tries a different strategy. He cannot push the rope, okay? But when he begins to wave it up and down in a steady, regular motion, a curious thing happens. A continuous wave pattern appears along the entire length of the rope, as you can see in the right figure. In fact, the waves means each representing one up and down cycle of the sender's arm actually travel from the sender to the receiver. This is sending a continuous wave down a rope. In free space, a similar principle occurs. The sender, a transmitter, can send an alternating current into a section of wire, an antenna, which sets up moving electric and a magnetic field that propagate out and away as traveling waves. The electric and magnetic fields travel along together that and are always at right angles to each other, as you can see in this figure. We have electric field and magnetic field. Okay, this is the antenna, and when we send the electrical signal, we will have electric field and also magnetic fields that are always at right angles to each other. The signal must keep changing or alternating by cycling up and down to keep the electric and magnetic field cycling and pushing ever outward. Electromagnetic waves do not travel in a straight line. Instead, they travel by expanding in all directions away from the antenna. To get a visual image, think of dropping a pebble into a pond when the surface is still. Okay, where it drops in, the pebble sets the water surface and into a cyclic motion. The waves that result begin small and expand outward, okay, only to be replaced by a new waves. In free space, the electromagnetic wave expand outward in all three dimensions. This figure shows a simple idealistic antenna that is a single point at the end of a wire. Okay, the waves produced expand outward in a spherical shape. The waves will eventually reach the receiver, in addition to many other locations in other directions. This idealistic antenna does not really exist, but serves as a reference point to understand wave propagation. In the real world, antennas can be made in various shapes and forms that can limit the direction that the waves are sent. At the receiving end of a wireless link, the process is reversed. As the electromagnetic waves reach the receiver's antenna, they induce an electrical signal. If everything works right, the received signal will be a reasonable copy of the original transmitted signal. Alright, now let me to explain a little about the frequency. What is the frequency? The waves involved in a wireless link can be measured and described in several ways. One fundamental property is the frequency of the wave, or the number of times the signal makes one complete up and down cycle in 1 second. Actually, it means that in 1 second, how many complete cycles are available. This figure, as you can see, shows how a cycle of a wave can be identified. A cycle can begin as the signal rises from the center line, falls through the center line, and rises again to meet the center line. For example, here, as you can see, this wave rise to the up and then down to the center line, and after that again down and then up. Actually, as you can see here, in 1 second we have 4 complete cycle. Look at here, 1, 2, and then 3, okay, and finally 4. Because of that, we can say here we have 4 cycles per second, or 4 hertz. Instead of cycle per second, we can say hertz. Actually, a cycle can begin as the signal rises from the center line, falls through the center line, and rises again to meet the center line. A cycle can also be measured from the center of one peak, okay, to the center of the next peak. And after that, we can say the frequency is the number of times the signal makes one complete up and down cycle in 1 second. No matter where you start measuring a cycle, the signal must make a complete sequence back to its starting position, where it's ready to repeat the same cyclic pattern again. In this figure, suppose that 1 second has elapsed. As you can see, during that 1 second, the signal progressed through the complete cycles. Therefore, its frequency is 4 cycles per second, or 4 hertz. A hertz, or Hz, is the most commonly used frequency unit and is nothing other than 1 cycle per second. Frequency can vary over a very wide range. As frequency increases by orders of magnitude, the numbers can become quite large. To keep things simple, the frequency unit name can be modified to denote an increasing number of zeros, as you can see in this table. For example, you know about the unit hertz. Abbreviation is Hz, meaning cycle per second. Also, you can say kilohertz, or KHZ, 1000 hertz, okay, and megahertz, MHZ, 1 million hertz, okay, and then gigahertz, GHZ, means 1 billion hertz, okay. Because of that, in most cases you hear about the hertz, kilohertz, megahertz, gigahertz, and maybe more. This figure shows a simple representation of the continuous frequency spectrum ranging from 0 Hz to 10 to the power of 22, as you can see, or 1 followed by 22 zeros Hz. Okay, at the low end of the spectrum are frequencies that are too low to be heard by the human ear, followed by audible sounds. Okay, the highest range of frequency contain light, followed by X, gamma, and cosmic rays, as you can see here. Okay, the frequency range from around 3 kHz to 300 GHz is commonly called radio frequency, or RF. It is so important for us. The frequency between 3 kHz, okay, from here, and to 300 GHz, okay, is commonly called radio frequency, or RF. About the RF, it includes many different types of radio communication, as you can see here, including the low frequency radio, AM radio, shortwave radio, television, and also FM radio, microwave, and radar. The microwave category also contains the two main frequency range that are used for wireless LAN communication. Here we have two main category, 2.4 gigahertz wireless and 5 gigahertz wireless. We use these two range, okay, these two wave range for the frequency for our RF or radio frequency communication. Because a range of frequencies might be used for the same purpose, it is customary to refer to the range as a band of frequency. We call band of frequency. For example, the range from 530 kilohertz to around 1710 kilohertz is used by the AM radio station, as you can see here. Okay, we call it, or therefore it is commonly called the AM band or the AM broadcast band. Okay, actually they range between 530 kilohertz to around